Okay, so hello and welcome back. So in this video we want to talk about the zeros of a polynomial. This is a continuation of the previous video, and basically let's say that as an example, in order to show this concept, let's say that you have some polynomial. For example, let's say that you have some polynomial, let's say p of x is equal to x squared minus 3x minus 4. Okay, let's see how this polynomial is doing at x is equal to -1 and x is equal to positive 4. Okay, so when x is equal to -1, then p of -1 is going to be equal to -1 whole squared. I'm putting -1 into this formula. Minus 3 into -1 minus 4, which is equal to 1 plus 3 minus 4, and that's equal to 0. So what that means is that p of -1 is equal to 0. That means that the value, the output of this polynomial at x is equal to -1 is 0. And on the other hand, when x is equal to 4, what happens is that p of 4 is equal to 4 raised to the power 2 minus 3 raised into 4 minus 4, which is equal to 16 minus 12 minus 4, which is equal to 16 minus 16, which is equal to 0. So that means that the output of this polynomial at x is equal to 4, or p of 4, is equal to 0. Now these two numbers over here, x is equal to -1 and x is equal to 4, that these two numbers at which the output of your polynomial goes to 0 is actually are actually called the zeros of this polynomial. So -1 and 4 are the zeros of the polynomial p of x is equal to x squared minus 3x minus 4, because the output of or the value of p of x is 0 at those two numbers. At those two numbers used as x. That is p of -1 is equal to 0, and also p of 4 is equal to 0. Okay, so that's basically the meaning of the zeros of polynomial. And moreover, if you actually do the graph of this function x squared, whatever that was, x squared minus 3x minus 4, if you do the graph of this function, this is going to be something called a parabola. And what that is that it's very simply a it's very simply, for example, if you do the graph of this function, that would be, for example, let's go to desmos.com and do the graph of this function. And that was x squared minus 3x minus 4. I write this as f of x. I write this as f of x is equal to x squared minus 3x minus 4. And as you can see, this is a parabola. This is basically a parabola that, and this is the general form of the graph of this polynomial, you could say. And you can say that the polynomial goes through the x-axis at x is equal to 4 and x is equal to -1. And of course, if you think about basically these 2 points, basically this point is 4, 0, and this point is -1, 0. That means that at -1, of course, the output of your function is 0, otherwise that would not be the x-axis. And at x is equal to 4, of course, the output of your function is 0, because otherwise that would not be the x-axis. So that's basically the graphical meaning, or the geometric meaning of the zeros of a function, meaning that the zeros of a function are basically the points where the graph of the not the function but the polynomial actually goes through the x-axis, right? So now those 2 points for this polynomial are -1, 0 and 4, 0. Okay. Now if you take those 2 points for this graph, where basically something like this, so you had a graph like this, and that was -1, 0, and then that was 4, 0, and the graph was basically a parabola like this. So it was some parabola like this. Okay, something like this. There is a lower limit for your output here somewhere. Your function has a minimum over here, and it has no maximum over here. It goes all the way to positive infinity. But this point over here and this point over here, this is -1, 0, and this point over here is positive 4, 0. Okay. And you see that at both of these points, since both of these points are located on the x-axis, the output of the function in both cases is 0. So that means that, of course, any point that you find on the x-axis, at those points the output of the function is 0, because well, it's on the x-axis, basically inherently the output of the function is always equal to 0. So and so basically any such points that you might have related to the graph of a polynomial, the x-intercept of these points are called the zeros of this polynomial, meaning that the zeros of this polynomial are -1 and 4 over here. So that's basically the whole story here. Now in order to, so now based on the fact that we know that basically the zeros of the polynomial are the x values for which the output of the function is equal to 0. Okay, so now based on the fact that we know that basically by definition, we can call it the definition, for example, that we know that by definition we call these points, these 2 points, -1 and positive 4, the zeros of the polynomial, and those points are basically kind of points where the output of your function is 0. Otherwise, if you take a look at the whole graph of this function, at any other x value, your basically output value is either a positive value or a negative value, and only at these 2 points is the output of the function equal to 0. Okay, so based on that, what you can do is that you can actually set in the polynomial itself, you can set the output of the polynomial equal to 0, and then find the x values for which basically at which that phenomenon happens, and that becomes basically, and the points that you find there are going to be the zeros of the polynomial, meaning that your polynomial was x squared minus 3x minus 4. X squared minus 3x minus 4, that was basically, you can call this p of x or whatever you want to call it. So let's say that your polynomial was x squared minus 3x minus 4, right? So now you want to find the zeros of this polynomial, meaning the x's for which the output of this polynomial is equal to 0. So if the output is equal to 0, that means that p of x is equal to 0. But p of x is equal to x squared minus 3x minus 4, and that is equal to 0. And so basically what that means, if you set the polynomial equal to 0, that basically is going to give you all the different x's for which or at which basically this phenomenon basically can happen. And so in order now you have a simple equation to solve, x squared minus 3x minus 4 is equal to 0. In order to solve this equation, you need to factorize the second degree polynomial. And you know how to factorize these kinds of equations. So you have, in order to factorize this, what you can do is that you have to find a way. So let's say that you have x squared minus 3x minus 4 is equal to 0. You want to factorize this thing, meaning that right now it's a second degree polynomial. You want to write it as the product of two basically first degree polynomials. For example, x minus a times x minus b is equal to 0, something like this. And then if x minus a times x minus b is equal to 0, then what that means is that if the product of these two is equal to 0, then what that means is that either x minus a is equal to 0 or x minus b is equal to 0. Otherwise, their product could not be equal to 0. And what that means is that x is equal to positive a, and here x is equal to positive b, and those are the two zeros that you are basically looking for. So now in order to be able to, and as you can see, both of these, both x minus a and x minus b each of them is a polynomial, but it's a first degree polynomial. But over here I have a second degree polynomial. So now in order to be able to do this, what we usually do is that we have to basically rewrite this middle term over here in such a way that you can actually kind of you basically, for example, negative 3x, for example, negative 3x, what you can do is that you can write it, for example, as negative 4x, right, plus an x, right? So negative 4x plus x is equal to negative 3x. So that's positive 1, negative 4x plus x is equal to negative 3x. So now if I rewrite this, if I use, for example, this, now this was something easy, I could simply see it, but it's not always easy, and for the same reason we have some sort of techniques in order to do the same thing. We will get there, of course, and I'll show you how to do that as well. But now let's say that negative 3x is equal to negative 4x plus x. So I can write this as, based on this, I can write this as x squared, and instead of negative 3x, I'm going to write it as negative 4x plus x. And then I have a negative 4 over here, that's equal to 0. Now as you can see, there is these two terms over here, negative 4x, negative 4, and then there is these two terms over here. So if I take these two terms and take an x out, that would be x plus 1. And if I take these two terms and take a negative 4 out, I'll get x plus 1, I suppose. Negative 4x, negative 4x, and negative 4. And that's equal to 0. And then if I take basically x plus 1 out, if I take x plus 1 out, that would be x plus 1 times x minus 4 is equal to 0. So that's going to be x plus 1 times x minus 4 is equal to 0. That's exactly the kind of thing that we were talking about. So that's x minus a times x minus b is equal to 0. And now what that means is that x, either basically because the product of these two polynomials is equal to 0, either x minus a is equal to 0, or basically x minus b is equal to 0. Okay, so so that's what I want to do over here. So I write this as x plus 1 times x minus 4 is equal to 0. So either x plus 1 is equal to 0 or x minus 4 is equal to 0. So here x is equal to negative 1, or basically x is equal to positive 4. X is equal to negative 1 and positive 4. And that's exactly what happened even over here. You see x is equal to negative 1 and positive 4. So that's basically very simply how to find the zeros of this polynomial. Now we will get to more complicated examples. Now I could very easily rewrite this middle term as a sum of two terms, and then the two terms also happen to be appropriate in this context, and so I could use it in order to factorize this polynomial. But like I said, it's not always that straightforward, and we need to, and there are simple ways in order to actually do this and get to the factors of your polynomial. Now one more thing that I could still talk about here is the let me actually take a few minutes rest. I'll be back with you with the rest of this. Okay, so now there are some relationships that exist between basically the coefficients of in some polynomial and the zeros of this polynomial. And by the way, these zeros are also sometimes called the roots of the polynomial. Instead of saying 0, you can say the root of the polynomial. And then basically we said that if you have a first degree polynomial, which is called actually a linear polynomial is generally in the form ax plus b plus ax is ax plus b, basically. That's a first degree polynomial, and it's called a linear polynomial. Linear polynomial. And of course, if you do the graph of such linear polynomials, let's say that, for example, let's say that p of x, for example, is equal to 2x plus 3. The graph of this polynomial would be equal to some line. It would be basically it would actually be just a straight line. It would just be a straight line, and this number over here, we will get to this in future videos, but now that we are here, I can tell you a little bit about these numbers over here. It's good to know about them. So this number over here, that is actually your constant in a linear polynomial, this is called the y-intercept. This is called the y-intercept, and what that means is that it's actually the point where the graph of this function, the function of this polynomial, goes through the y-axis, meaning at this point 0, 3, this graph, the graph of this polynomial is going through the y-axis, meaning that would be 1, 2, and 3. So that would be one point of the graph of this polynomial. The other point you can figure out based on the slope of the polynomial. So this number over here, the coefficient of the variable, is called the slope. The other point you can figure out based on the slope of the polynomial, because as you know, any line, any straight line has some sort of slope. For example, if you have this line over here, this has some slope to it, and then you could draw this line. The slope of this line is higher, 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 the slope of this line is still higher, and this line is higher, and the slope of this line is undefined if it's a completely vertical line. And then if it's a completely horizontal line, the slope of that line is 0. Okay, so that's about the slope of lines. So any sort of straight line has some slope to it. And relative to that slope, something interesting that happens is that you will have some amount of change in your y with, for example, a unit change in x. For example, you see in this horizontal line that, for example, if I pick this x1 and this x2, then at this point over here, the value of the output of the function, or the output of the polynomial, is actually, you could call it y1, this point over here, and the value of the output of the polynomial at this point is also y1, meaning that, and that happens because basically it's a horizontal line, so there is no slope, and so the output is not actually changing. It's just a constant line. It's just a constant output. So that's basically, and then, for example, if you come to this function over here, or this polynomial over here, if I take the same x1 over here and the same x2 over here, so this is x1 and x2, you see that relative to x1, at x2 you have some sort of elevation for the output. At x1 my output was at this point. At x2 my output is at this point. So there is this elevation over here. Or there is some sort of negative elevation, which means that, for example, this point will end up somewhere over here, and then relative to that you would have, for example, some line like this, in which case the slope is said to be negative. Means that the elevation would be negative. So then what that means is that if you have the slope of a line, and if you have one point on related to that line, which is basically the case over here, then based on the slope you can figure out the second point. And that's what that's what I want to do right here, meaning that you have this polynomial. I know that based on the y-intercept, I know that one point is basically 0, 3, which is this point over here. The other point is going to be the other point you can figure out based on the slope. And the slope, what it tells me, it tells me actually for a unit horizontal change, how many units of vertical change there is in the function, meaning that it's always the rise, over the run, and that's equal to the slope of the function. So, for example, if your run is equal to 1, meaning that your horizontal change is 1, let's take this as 1 unit, and then that would be, let's say that this is half unit. So let's call the distance between x1 and x2, let's call that 1 unit, and this distance over here, I call it 1/2 of x, 1/2 of, for example, call this a units, for example. The distance between x1 and x2, I call it a units. And let's say that this distance over here is half of that distance. Okay? So then the rise in my function is half of that distance. Is actually half of that distance. So now over here the run is a units, because that's the horizontal change over here, and the rise is 1/2 a units, and then if you cancel out the a's over here, you will get 1/2. That means that the slope of this line is simply said to be 1/2. Okay. Or if you had, for example, if a slope of a line was basically, if the slope of the line was, for example, something like 1 unit, in that case what would happen is that if let's say that the slope of a line, which is usually denoted by m, let's say that slope is equal to 1. That means that your rise over your run is equal to 1. Okay? So that means that for one unit of horizontal change, you have 1 unit of vertical change. That means that if you had a graph would look like this, let's say that, for example, this would be a point on the graph of the function. So then the next point would be basically, this is basically one unit of horizontal change, and then basically this would be a unit of vertical change. So if I have 1 unit of horizontal change, I will have 1 unit of vertical change. That would be the second point on the graph of the function, and basically then you can say that the slope of this line is equal to 1. Meaning that for 1 unit of horizontal change, you have 1 unit of vertical change. And that's what the slope is. It tells you a lot about change and the rate of change and so on and so forth. We'll get to that hopefully soon. So basically then, I don't really know why I started talking about all of this, but I sure hope to wrap it up soon. So then you have, for this function, you see that the slope is 2, meaning that for 1 unit of horizontal change, you have 2 units of vertical change. So if I take this as 1 unit of horizontal change all the way up to here, I will have 2 units of vertical change. So that is basically that you could think of this as as a triangle where this is 1 unit and this is 2 units. Two units of vertical change, 1 unit of horizontal change, and this vertex of this vertex would be the second point on the line. And the interesting thing is that the slope of the hypotenuse of the triangle is actually the slope of the line. So you see over here, that's going to be your line. And oh, I got it. I wanted to show you that a linear polynomial actually goes through the x-axis only in one point. Okay, so now you got only one point over here. And that is basically called the x-intercept of this point. The x-intercept of the point is basically the zero of the polynomial. Okay, so now how can you figure out what this zero is? So you know that at this point the output of the polynomial is actually equal to 0, because this height over here on the y-axis is actually 0. So if I set the output of this polynomial to 0, meaning that p of x is equal to 0, that would mean that 2x plus 3 is equal to 0. That means that 2x is equal to negative 3, x is equal to negative 3 by 2. And that's the x-intercept of this point over here. And if you pay attention to the number that you got over here, you see that this thing over here, we said that the general form of a linear polynomial is ax, this is a, and this is b. This ax plus b, and this is in the form, this x is in the form basically negative b by a. Okay, so that means that the zero of a linear polynomial is basically of a linear polynomial ax plus b is that you can actually calculate it by negative b by a, and that's basically the relationship between the coefficients of the coefficients in a linear polynomial and the zero of the polynomial, meaning that in general, if you have a polynomial p of x is equal to ax plus b, and if k is a zero of that polynomial, then if k is a zero of that polynomial of p of x, then p of x is supposed to be equal to, then p of k is supposed to be equal to 0, meaning that p of k, which is equal to a times k plus b, is supposed to be equal to 0. So now ak plus b is equal to 0, so k is equal to negative b by a. Okay, so what that means is that if you have a linear polynomial p of x, ax plus b, and if k is a zero of the polynomial, so then you can express that zero as negative b by a, and that's basically the relationship between the zero of a linear polynomial and the coefficients of these two coefficients a and b, basically. So basically the zero of a linear polynomial is related to its coefficients, and that's basically the relationship there is here. And this relationship also exists between the between the zeros of a for example quadratic polynomial, a second degree polynomial, and the coefficients in the polynomial itself. We will talk about that later. Okay. Okay, so now about there is a couple of things that we can do to show the geometrical meaning of the zeros of the polynomial. And what that is, I don't want to spend too much time over here, because I want to get this, because I just want to I want to wrap this up as soon as possible. I don't want to spend much time over here, because I have already done many courses related to these functions and I don't know, the graph and so on and so forth. But still, I want to talk a little bit about the graphical meaning of the zeros of a polynomial. And the first thing that we can do is basically show the graph of a first degree polynomial, which is basically a linear polynomial. And that would be something like, for example, this polynomial over here. For example, if you have let's say that you have a polynomial. Let's say that when you talk about linear polynomials, they are in the form basically ax plus b, where basically a is not equal to 0. Otherwise, you would have only the constant term. And if you want to draw the graph of this polynomial, you could write it as y is equal to ax plus b, and this is going to be a straight line. For example, if you have y is equal to 2x plus 3, the way that you can do the graph of the function without depending much on the y-intercept and the slope of the function is that you can simply put together a simple table of input outputs for the function. So for example, you could create this thing over here as x and y, and this is some inputs for this function and some outputs for the function. And for example, you can let's say that, for example, if x is equal to 0, then your output is going to be equal to 3. Okay, so, and that's basically what we talked about as the y-intercept of this function, meaning that this point would be 0, 3, which is basically some point on the y-axis. And then you could pick some other point. For example, I don't know, if x is equal to 1, for example, then you would have 2 times 1 plus 3, which is equal to 5. And so this point would be 1, 5, and then you would be able to draw the graph of this function like so. And it would be 0, 3, 1, 2, and 3. This would be 1 point, and 1, 5 would be 3, 4, and 5. This would be the second point, and then this would be the graph over here. And you can see that it's a completely straight line going through this point. And this point is actually the x-intercept of the function, meaning that if you do this to proportionally, what you would get is basically 2x plus 3. So if your f of x is equal to 2x plus 3, for example, it's going to be, you see this point over here where the graph goes through the x-axis is negative 1.5. So this point over here is going to be negative 1.5. Okay. And there are a few things that you can note over here. First of all, what you see over here is that the graph goes through the x-axis at only one point, and that point is actually the zero of the polynomial, meaning that we said that the zero, if k is, we said that if k is the zero of a linear polynomial, okay, then p of k of a polynomial, basically p of x, for example, then p of k is going to be equal to 0. That means that if you input that, if you input the k into the equation as an input, then your output is going to be equal to 0. And negative 1.5 is the same thing as negative 3 by 2. Okay, so, and if you input this into this equation over here, if let's say that this is p of x is equal to 2x plus 3. Now, if you have p of x is equal to 2x plus 3. Now if you calculate, for example, p of negative 3 by 2, p of negative 3 by 2, you're going to have 2 times negative 3 by 2 plus a 3. And these two will cancel out. You have negative 3 plus 3 is equal to 0. So that means that negative 3 by 2 is actually the 0 of this polynomial. So, so basically, in general, for a linear polynomial ax plus b, where a is not equal to 0, the graph is the graph of y is equal to ax plus b is a straight line which intersects the x-axis at exactly one point, namely and the coordinates of this point are going to be your is going to be basically this x-intercept over here, which is negative b by a, right? Because we said that, if you remember, we said that our polynomial was p of x is equal to ax plus b, okay? And if k is the zero of the polynomial, that means that the output of this polynomial at k is going to be equal to 0. That means that p of k is going to be equal to ak plus b is going to be equal to 0. And if ak plus b is equal to 0, that means that k is equal to negative b by a. Okay? And that is basically, and what that means is that at this point k is equal to negative b by b. The output of the function is going to be equal to 0, and what that means is that the coordinates of this point is going to be negative b by a, comma 0. Okay? So that's basically the whole story here. So therefore, the linear polynomial ax plus b has exactly 1, 0, and then that's the whole story. Okay, so the next thing that we have here, that's all you need to know about. I mean, that's all we need. That's all we actually have so far about linear polynomials. Now, there is some other type of polynomial which is a second degree, which is a polynomial of degree 2. Which is basically called the quadratic polynomial. Okay, and this quadratic polynomial is the general form of this type of polynomial is ax squared plus bx plus c, and here a is not equal to 0, otherwise the degree would be at most 1, not 2. And the graph of this kind of polynomial is called as p of x, for example. the graph of this polynomial is going to be y is equal to ax squared plus bx plus c. And as an example, you could have y is equal to x squared plus, for example, 3x, take it as minus 3x, for example, minus 4. And then in order to get some values for this polynomial, you could again do some simple table, for example, some table of values x and y. If x is equal to 0, for example, you have your output is negative 4. If x is equal to 1, for example, your output is going to be equal to, I don't know. But in the case of these functions, you need at least 3 points, because it has these kinds of functions have kind of a peak, a curve in them, and they are symmetrical about some point, so you need to find that point. And it's a parabola, basically. And I'll show you how to actually do that. So how that you need to find some sort of maximum or minimum for the function, and so on and so forth. But let's see how this function actually behaves. So for example, at x squared, you have at x is equal to 1, the output is going to be 1 minus 3, so that's negative 2, negative 6, for example. Now there are many different ways. That you can actually analyze, for example, this function over here, and analyze this function over here, and then based on that do a graph. For example, we know that, for example, these parabolas ax squared plus bx plus c are depending on the polarity of this coefficient a here. It's either a function like this, for example, it's either a function like this or a function like this, meaning that upside down, or meaning that it either opens upwards or downwards, and that depends on the coefficient of x squared. If a is basically a positive number, it's going to be opening upwards. If it's negative, it's going to be opening downwards. Okay, but then in order to not have to try many points over here, you need to somehow find this peak over here, either this peak or this trough over here, and then basically try some points around that point, and then that way you get the symmetry and everything related to that function. Then you will be able to draw it. And well, most of those, but in order to get this point, which is exactly about which the graph is symmetrical, you need to have some information about these parabolas, which we do not still have, okay, at this point. And you can also do it using calculus and all that kind of thing, which is right now not very practical. So what you can do is that if this function goes through the x-axis, if it's either in this form or the other form, doesn't matter, but if this function goes through the x-axis, it will have basically 2 zeros, meaning that it goes through the x-axis at 2 points. If you can find those 2 points, then there is a way to actually go between those 2 points and find this point over here, which is exactly in the middle of the 2 zeros, basically. So what I'm going to do is basically go and factorize this. I'm going to factorize this polynomial, and this is a second degree polynomial. You can factorize it into 2 first degree polynomials, into 2 linear polynomials. and then based on that you can find the zeros, and then based on the zeros you will be able to find some point of symmetry either at the peak or at the trough, and then you'll be able to draw the graph of the function. But before I do all that, I need to take a few minutes rest. Okay, so I will end this video here. In the next video we will start working on this thing. I'll see you in the next video. Thank you.